Começa agora o podcast Atômico. É um oferecimento de RDC Brasil.
Hello everybody. So today is a different podcast. It will be in English at the beginning. Later it will be translated for Portuguese. But it's my pleasure. It's a very big pleasure to have here you all that are assisting the Atômico podcast. And there is joining to us, we have Dr. Tadashi Narabayashi. He's a professor at the Tokyo Institute of Technology, specializing in advanced nuclear energy and reactor safety. And also we have Dr. David Miller, adjunct, sorry, my bad, eventually poor English, but I will not switch for Portuguese. Later we will, after the meeting. Yep. And the adjunct assistant professor at the University of Illinois, Urbana-Champaign, and the leading expert in radiological protection and occupational exposure. Also, we have the brilliant journalist Isabela Fleischmann, do Amaral, who holds a master in business and economics and reporting from New York University, also joining me to interviewing them. That's a very important approach because what's the idea behind that? One person that is not so skilled in nuclear area, but very skilled in economics, will bring to us the point of view of a person outside of the production of nuclear energy, but also the person caring about the profits, about the productivity, about the importance of nuclear energy in terms of economics. So that's the idea. Isabela joining us, and that's my thank to all of you. So thank you very much. And to start, I would like that each of you, could briefly describe how you become involved in nuclear engineering. So if you could. So I give the floor first to David, but Tadashi will be our main speaker. David and I will be supporting him, but he is, because the topic is from Fukushima, post-Fukushima. So Tadashi is the person that will be leading this presentation. And we will be performing questions, supporting him, things like that. So David, could you say some words, how you joined to nuclear, please? Some days ago.
Thank you. Thank you. Very nice to be here, and welcome. It's very nice to be here with the distinguished professor, Tadashi Narabayashi and Marcos. And I am very pleased to be here to share that my interest in nuclear started when I graduated from Purdue University. I went to Sergeant Lundy Engineer, and we designed the 7 power plants in Illinois in the 70s, and they're all operating very well now. We designed them for 40 years, and now they're being allowed to go to 60 to 80 years. We're even restarting a plant in Palisades, just north of us. I was privileged to be the startup manager for environmental and RP and emergency planning at Susquehanna in Pennsylvania, 2 BWRGs, and then also the startup director of radiation protection at Clinton Power Station, and finally at Cook Power Stations in Michigan. At that time, I became director of the North America Technical Center, which is a Canadian, Mexican, and U.S. utilities under the IAEA OEC program of Information System on Occupation Exposure, where I graciously was able to work with Marcos, who was our bureau chief for many years with the ISOE program, again, the Information System on Occupation Exposure. You can learn about it at isoe-network.net. Thank you. It's a privilege to be here. I'm looking forward to Professor Narabayashi's presentation.
Thank you. Tadashi, please, Professor Narabayashi, I will use Professor Narabayashi, even that we are nice friends, very nice friends. We all, guys, we are very nice and long-time friends. But Dr. Narabayashi, please, could you give you a brief description? Okay, if you prefer to start now the presentation, it's up to you. But
Okay.
just hold a bit. Isabela, do you want to say something?
No, I just want to say that it's great to be here among these great professors and specialists in their areas, and I hope that I can bring something to the discussion.
Thank you.
Thank you. So the words are with you. Please, Tadashi, feel free to develop in your presentation. Later on, we will come back and make several questions and also give to you questions coming from the public, just in case. Go ahead, please.
Yes. This shows the largest earthquake ever recorded in Japan, March 11, 2011. Great East Earthquake, Japan. The very, very strong earthquake, magnitude 9.0. This shows the scenery soon after the tsunami and earthquake and tsunami at the Onagawa towns.
So we will be focusing on Nagawa, right?
Yes. Yes. This shows the yes. This is a 56 Emperor Seiwa. At the Jogan tsunami occurred 869. And there are 4 big earthquakes before the March 11.
No, go ahead. Go ahead, please.
Okay. And Emperor Seiwa ordered, do not take any tax from these areas attacked by the tsunami.
That's good. That's good. So Tadashi will not be translating online, so
And
feel free to proceed in English. We will
and
only make
this,
some comments. Okay.
Onagawa nuclear power station here, very nearest power station at the epicenter of the earthquake. And there are several nuclear power stations on the coast. The Onagawa and Fukushima Daiichi, Fukushima Daini, and Tokai Daini.
Okay.
Onagawa 1, 2, 3, external power and seawater pumps were alive.
Okay. They don't lose. They don't lost. They didn't lose.
Unit 1, 2, 3, all the nuclear power plant in Onagawa station. Shut down okay, cool down okay, and contain the radioactive materials okay. So, because nuclear disaster prevention training was also carried out at Onagawa Nuclear Power Station. And the residents of Onagawa town damaged by the tsunami arrived at the PR center. They guided everyone to the gymnasium and spent 3 months in a vacation shelter. And the Tohoku Electric Power Company received a nuclear contributor award from WANO. And also, IAEA report, remarkably undamaged.
Okay. So one point, very, very important point here is that
And
Onagawa
the general
power
meeting
plant.
of the determination include the people in Onaga town to complete the safety measures, construction, work for the Onagawa Unit 2. Last year, December 20, they started 2022, and they started last December, last year. The fisherman joined the restart training. They are both one team Onagawa. And the Onagawa nuclear station, a lot of cables and earthquake, anti-earthquake support. This is a support. And also the gas turbine generator car and the large capacity pump car. So, and also the Shimane Unit 2 started commercial operation. And the Unit 3 of the Hokkaido Electric Power Company, Tomari Nuclear Power Station will be start. And also it is very important to support the IAEA comprehensive report to the tritium related water. And today, another point to the just before the Tokyo metropolitan area, just before blackout, March 22, 2022, 35 million people live at the metropolitan area. There are
Yep.
a lot of huge number of solar panels, but cloudy, snowing, cloudy, very cold, lost 12.5 gigawatts. It's correspond
Just
to
because there were no sun, and
sun,
then
and
no sun,
and
no
some
power.
snowing at even the March 22, very cold. So just before the electricity demand increased. No
So
sun, no sun.
just a minute, Tadashi. You say that 3.5 gigawatt were reduced, were lost due
Lost.
to the cloudy weather and the lost cool
Weather,
also power.
cloudy and snowing.
My incredible. Yep. Please go ahead. Go ahead.
So it's terrible. The sunny day, 40.3 gigawatt, but cloudy, only 1.7 gigawatts.
It's a
So
huge loss.
he's lost. It's dangerous.
Yep.
Solar panel is dangerous to cause of the blackout. And the Japanese nuclear power plant reduced the risks. By using a filter containment system, the loss of ultimate heat sink TW sequence reduced 3 orders. And the total core damage frequency also reduced.
1,000.
1,000.
Yeah. By 1,000.
Nuclear power plant is very, very safer than before the March 11. And also the lot of merits install the filter containment system. Lot of people only stay in house.
Okay.
And this shows the carbon dioxide emission per kilowatt hour grams per kilowatt hour. The best solution is hydro and nuclear. This Norway, Swiss, Sweden, France, and Canada, very low carbon dioxide emission. Then the wind company, country, Belgium, United Kingdom, Australia, Spain, and Denmark. But United States, Germany, Japan, China, India, the very huge amount of the solar panels, but it's not effective. This shows the destruction of nature in Japan caused by solar panels. Huge green trees in the forest cut down to install the solar panels. Very huge amount of solar panels installed in Japan. And this shows the increase of extremely hot days with maximum temperatures of 35 degrees Celsius or higher in Japan. After March 11, 2011, the number of the hot day is increased. Because solar panels at the summertime, surface of the solar panels exceed 80 degrees Celsius. It's almost the same as the desert sand surface, 80 degrees Celsius. So in Japan, increasing of the solar panels causes the heat up the air.
Okay.
And hot air goes up, and it affects the jet stream. By the jet stream north, and the hot air over the Japanese areas cover the hot air, and also the high humidity steam supplied by the hot sea. So nowadays in Japan, hot summer and also the very huge rainfalls. The right
So
of
you
the-
say that the installation of solar panels for photovoltaic panels, they are increasing the temperature as well because they are reducing the jet stream of the air. So I mean, they are concentrating heat, if I could say like this, and with this, in one sense, you produce power to use air conditioners, but then you have to use air conditioners because you produce power by using solar panels.
Yes.
Is something like this, if I understood well, Dr.
So the hot
Tadashi.
summer increase the demand of electricity by the air conditioners. And the air conditioners also the heat source.
Right.
So in Japan, rise of global average annual temperature coincide with installation of the solar panels. Japan's temperature rise is 3.8 times the global target. This 2025, this year, hot summer.
The hottest, yeah.
So the solar panels annual supply share, this is only the it corresponds to the capacity factor, only 13%. And also the wind 25%. So 100% to supplying electricity solar panels shares annual supply share only 13%. Also the wind supplying 100% electricity, only 25 share. A total 200 power, the solar and wind. Total is only 38%. But cloudy and no wind. It's a solar panel and wind almost zero. So Japan needs hydro, nuclear, and thermal. So 100% can supply the electricity, hydro, nuclear, thermal. So by increasing the that's a type of the eco energy, solar panels, wind, and also the 100%, almost 300% electricity sources needed. But you can easily understand hydro, nuclear, thermal can supply 100% electricity. So solar panels and wind does not need anymore. It is very, very important. So the safety increased nuclear power is very, very important. So I will developing the load following SMRs to replace us thermal powers. So in the future, all the electricity supply nuclear power plants and also the hydro. I think this is the best solution. So it is a introduction, my presentation.
Thank you, Professor Narabayashi, for
Yeah,
this.
just could you move for the next page for the conclusion? Just to get the conclusion. Yes. Then you please point out your conclusion here, and then we will go talking. There are some other points that I would like to touch with you.
Yes. From the lesson of Fukushima Daiichi accident, Japanese nuclear power plant has installed safety measures and 14 nuclear power plants restarted. BW's Onagawa second, Shimane second start commercial operation. Kashiwazaki Kariwa 6 and 7 needs a local government agree. And Kashiwazaki Kariwa Unit 6 will restart next January 20. Green transformation, GX, which aims the shift to the decarbonized society. Nuclear power plants should be utilized to the maximum possible extent. Decarbonation, stable supply of energy, and economic growth. We thank the nuclear radiation production experts and the ISOE members for support to restart the stable operation by policy ensuring safety and ARARA. Thanks to David. This is a young engineer.
Yeah, we'll touch about that. We'll talk about that. So, wonderful. You
And
please
also
could you?
the advice
Oh, go
of the
ahead.
NLC and the young engineer have talking.
This is great. Very detailed. I just want to ask a question for the ones that are not so familiar with the terms and nuclear energy. And from what I understand is that nuclear energy is way better than um, uh, the other types. You mentioned solar. It's the key for prevent global warming. But for the ones that are concerned about accidents like Fukushima, and the ones that only know Fukushima from headlines, could you walk us through, in simple terms, how the accident happened and if it could have been prevented in any way? Thank you.
Yeah, I don't know if you will keep the presentation on the screen. Yes, you could. You can, because then you can use to give your answers. Yeah, it would be better, right, Davey?
So, so at the Fukushima Daiichi nuclear power plant accident, the caused by tsunami. If soon after the earthquake, the emergency diesel generator started and supply the water to cool down. But after 40 minutes ago, after the huge tsunami attacked the Fukushima Daiichi. So the emergency generator lost by tsunami. And also the ECCS systems, pump, supply water, cooling water pumps damaged. And also the no heat sink to remove the decay heat is lost. That's the cause of the nuclear severe accident at the Fukushima Daiichi. But
Could have
Onawa nuclear power plant
Mhm.
attained cold shutdown. This is because the level of the ground, the site elevation. Tokyo Fukushima Daiichi nuclear power plant only 10 meters. And Onawa nuclear power plant, the meeting has conducted with the Tohoku University, the professionals of the earthquake and tsunami. They know the Jogan tsunami. So Tokyo Electric Power Company decided the elevation 15 meters.
Of the wall.
This difference of the 50 meters changed the other result. Protects the severe accident on the destroyed by the loss of electricity, emergency generator, and meltdown occurs at the Fukushima Daiichi. So this is a 5 meters difference.
Yes, and
Yeah,
I
and
may add that there were some remarkable engineering good practices that occurred in those first few hours. For example, they needed to have offsite power, and on the 4 units just north of Daiichi, they were able to reattach the cables in 46 hours, and they needed to do it within 48 hours, and that saved the 4 units there by remarkably manually restringing the offsite cables. The other remarkable thing was the chief operator engineer at Fukushima asked his engineers to go out to the parking lot where there were over 100 automobiles with batteries, and they harvested the batteries and put 10, 12 volt batteries together to get 120 volts, and were able to move certain valves in the control room by putting the batteries from automobiles in series. That's remarkable to think, be able to do that in the dark in the early hours after the tsunami and earthquake.
Yes, and I could say that it was a heroic act from Fukushima employees. I mean, all the technicians, all the personnel there, they were heroic doing that. So several other things happened there that with very high creativity showed by the employees just to recover power and to open valves and to start to try to manage the emergent situation there. So, but for me, the most impressive thing, I mean, I know that there are lots of impressive things, but one of the most impressive is that in Onagawa, they sheltered all the population there for a long term. So because in the building there, it was filtered ventilation, so that protected the personnel, the public, in the nuclear site. That was great, right, Tadashi. So I think it is very impressive. Showed there in one slide. Yep. Yep. 3 months. You see, David?
Yes, and I think the vice president had a helicopter, and didn't he bring food and water daily into to provide food and shelter and blankets for all the local fishermen who were staying in the gymnasium? Isn't that right, Professor Narabayashi?
Yes. United States Navy, mothership comes from the United States, and they save a lot of people, and also does they receive food.
Right.
We talked about the good practice that happened, but looking back with everything that we know now, anything could have been better with the knowledge that we have today?
Could you repeat?
If with the knowledge that we have today, anything could have been done better during the accident? Because we talked about the good practice, the things that worked. Was anything that you think that could have been done in the accident or in the aftermath that could have been better?
I guess I can talk about that as well, because one thing that could happen better was the evacuation performed in the neighbor cities, just to save some micro receivers, very, very low dose. And they, for example, hospitals were evacuated, transporting sick people, the patients, for other places far from the area without need. That was a decision that was made to save some microsieverts. In fact, by evacuating personnel, it created a lot of problem. It could be done better. This is one reason to have a very good emergency plan and integrated emergency plan with all the stakeholders over the region affected, possible affected region, to make integrated decisions. So the decision to bring the neighbors, the community neighbors living there to the plant, that I mean the community people living close to the plant to be sheltered there, was a very nice decision because they were very close. However, other cities a bit far, so they evacuated without need. So that kind of decision was not good. So people probably, as I remember, some patients died because that situation, or not totally, but probably because that removal So you can say better, David, Dr. Miller, and Dr. Narabayashi about this. But as I remember, it was one of the worst decisions during the Fukushima accident. Yep. Do you agree?
I think the Onagawa plant, we were graciously able to visit a year later through the ISOE program, Professor Narabayashi, and it was amazing to me to see that all the underground piping had actually moved with the earthquake and did not experience any ruptures. There was like a subsidence of maybe 3 to 4 feet. So you saw the place where the piping was, but essentially the structural engineering design of the BWR there, Onagawa, was earthquake resistant. I would also say that the Wayno process and ISOE, where we shared information with Fukushima operators and management right away within hours, was set up by the late Walter Mismachi and Tadashi. And we have a standby tank at Dresden 2 and 3 and Quad Cities 1 and 2, which are sister plants to Fukushima. And that standby tank does provide water for ultimate cooling of the reactor, but we weren't able to communicate that as well and as quickly enough for the operators at Fukushima, which would have been another supply of cooling water. But that's been a lesson learned, that we provided the super engineer training by taking them to Dresden 2 and showing them that feature. That is another means to mitigate loss of coolant accident.
Right. So yeah, I guess we have just pointing out some features post Fukushima that were implemented. Dr. Miller just told some. Dr. Narabayashi is talking, and naturally, our public eventually is not so aware, because there is a lot of measures taken. So, for example, the containment of the reactor building. So it was really filtered, totally filtered. It was developed by Dr. Narabayashi. So this filtered containment system is FCVS, containment ventilation system. That's correct. So it was a huge work performed, and perhaps Dr. Narabayashi, you could show something about the features of this FCVS system. There are more. Huh? We will touch the other about super engineers. We will come back in some minutes. But please talk to us about the FCVS system that you developed. So.
This shows the Onagawa Unit 2 filter containment systems. And this green is the support, anti-earthquake support.
Huge amount
of anti-earthquake support. Because Onagawa nuclear power plant, the nearest power plant at the epicenter.
And I would emphasize that the whole world industry has benefited from this, because we now have all installed, and within 5 years, what we call Fukushima backfits. And that has been remarkably important, so that all 350 plants worldwide who chose to install those things have a port to provide external water immediately. That's on the outside of the building, or sources of water that may be available, and fire trucks, as was designed by Professor Narabayashi and his colleagues that are now in use, that can be bringing both water and generators that are mounted on trucks immediately to your site. In the U.S., we actually have two staging areas in Tennessee and in Arizona that maintain all this equipment that can be moved within 24 to 48 hours to a site to use the lessons learned from Fukushima for all 93 plants that are operating in the U.S. So that's been a significant benefit to the world industry, the sharing of technical engineering information and mitigation equipment, generators, mobile tanks of water, and pumpers that has been significantly improved the safety margin for accidents, severe accidents that Professor Narabayashi has explained.
That's great, Professor, because I believe we have nuclear power plants on the West Coast, right? When there could happen tsunamis or earthquakes in California. Do we have?
Yes.
Okay.
We have one remaining 2 units of Diablo Canyon. San Onofre down by San Diego has been decommissioned, although they wish they would have it now and restart it like many of our plants, which we'll go into later. Because of the data center demand, as Professor Narabayashi is experienced in Japan, we have an enormous appetite for more generation of electricity in the U.S. And so all that he is showing here has been factored into the design of up to 100 new 1,000-megawatt plants that are under the idea of building in the U.S. To handle the demand of data centers. I would note that the 3 Mile Island Unit 1 PWR, which is an excellent plant, it's been agreed upon with Microsoft to have it restarted to provide electricity for their data center. Clinton, which I had started in 1988, it is now has a commitment from Meta, and they may build the second unit that was never finished at Clinton. And then finally, Palisades is restarting in February of next year, and Duane Arnold in Iowa is being refurbished. So the value of these nuclear plants has become very, very important to meeting the huge increase in generation demands of data centers in the U.S.
That's right. That's a great point. In this era of AI, everybody is looking for energy. And so I just want to ask if this new technology, as I mentioned, AI, is there anything in this world of artificial intelligence and this new developed systems that can help nuclear power plants in any way? Is this new technology being used in these power plants to reinforce safety or in any way?
In Japan and also United States, NRC starts to examine the application of the AI technology to the nuclear power station. For example, some flow rate decrease.
Say again,
And
please.
AI announced the operator the flow rate reducing, watching. So it is very, very important to advise nuclear power plant operator some applicable advice, and also the prevents the accident.
Flow rates, cooling flow rates. That's correct. Yeah.
Thank you.
So
Yes,
yeah, I see it. Go ahead, David, please. Yes, Doctor.
I think
Dr. Miller, please.
from a privileged experience that I had in designing many of these plants, Byron, Braywood, and LaSalle, and Clinton in the 70s, with remarkable what we're able to do because we designed the plants for only 40 years. And now we plan to go 80 years. And so the key area is for us to monitor aging plant material condition. And that is critical. And AI has been set up to first, in normal operations, look at water chemistry for all particular sister plants like Byron braidwood or duplicate plants. And you look at their particular chemistry because that preserves their steam generators. Poor chemistry could require a replacement of steam generators too quickly. Or we also have the use of it for monitoring flow, as you're seeing. And then finally, the refueling outages that occur every 18 months for PWRs and every 24 months for BWRs, where you open up the plant. If you're costing your cells about $50,000 an hour, if you can save the critical path time, which we've proven we can do by using AI and big data. And in the case of Cook, we analyzed 10 refueling outages with work orders and our radiation work permits for each unit and looked at 3 million different time for work and dose and got the ideal work permit with the ideal work order because 85% of our outage work is repetitive, like reactor disassembly. And so we now freeze the best model for a work order of repetitive job and the RWP so that we can make sure we do an outage predictably within the 30 or 20 days in some cases. And in the case of Braidwood and Byron, they're down to 18 days of refueling outage, which gives us more availability of the electricity. In fact, in the last 10 years, because of the studies we've done based on the Japanese experience and our own, we have gone from 65% capacity factors to 92%. And that was the equivalent of not having to build 13 1,000 megawatt reactors. That's incredible because they cost $30 billion in the case of Vogtle 3 and 4. So we are learning with AI and by sharing worldwide our work practices to what we call optimized work planning for the outage and optimized monitoring of your aging plant.
Right. That is one thing that is very impressive, Dr. Miller, is the cooperation between Japan and the United States made by yourselves. So the engineers that were there for several years, learning, sharing, studying, and they became like you call super engineers, which in fact they are because are very broad expertise in nuclear. And this is one kind of cooperation that the world should learn because Fukushima happened there and worked very well. It was very resilient. Even that failed, but nobody died because of radiation, not to the accident there. And tsunami, about 19,000 people died there in Japan. It was very, very sad. But nuclear sustained it, like Onagawa brought the neighbors and protected them in their facilities. So, in its facilities. So, nuclear really have the ways to give to the world a very good protection and safety, and also maintain, because a huge capacity factor, sorry, and I need some water. But then this is very impressive, the cooperation that you had there. So under ISOE, under NEA-OECD, you, Dr. Miller, was the motor of this project. I know that. And Dr. Narabayashi, since the beginning, you were there. After, unfortunately, Mr. Mizumashi left us, but he left us with a lot of wisdom, a lot of information. So I congratulate you because that. I really want that your presentation be shared. It will be shared in Clearwater in January. I will be there with you. So all the information that you give to the nuclear world to make safer the nuclear energy, and not only nuclear, driving to other applications of the society, because nuclear is the most safe way to produce energy, and also the most ambientally correct way to produce energy. Unfortunately, people don't know. This is the reason why Isabela is here as well, to translate this in some way in numbers, which could be money, which could be economics, which also is the quality of the life of the people. So that's the very important. We are talking not only for nuclear, we're talking to the world. We're talking to say, hey, Fukushima is an example. The way they control the spread of radioactive material, the way they clean it, the way they are going until 2051, I guess, to completely clean that ambient, the way that nobody died, but despite the huge event caused to Fukushima. So the containment ventilation system is very, very important in my point of view. So the hangers and snubbers that were made to support the piping, the number of cables, very well protected cables that were huge amount of cables, the walls that were constructed between the sea, so there are more, the extra power equipments that were stored in the sites. So I mean that PWR, pressurized water reactor in Japan all returned to operate, I guess. And I think that BWR, boiling water reactor, Bravo water reactor, is very soon returning to operate in totality, or if not in totality, but in majority. And then after my long talk, I would like to give a question to Dr. Narabayashi. I remember that you gave a speech to Germany people, how it was and how they perceived that. Please, could you talk something about this speech there for Germany? Go ahead. Just give to us some idea about your speech to Germany regarding nuclear.
And Germany, all the nuclear power plants stopped. So for the only 1 year, the Germany's economy destroyed. Volkswagen factory in Germany should be closed because very, very expensive electricity increased the cost of the car. So it's a terrible situation at the Germany. So the Germany people asked to make a presentation to me. So how even the Fukushima Daiichi nuclear power plant accident occurred in Japan. How the nuclear power plant restarted in Japan? How do you ensure the safety at a lot of activities? Then Japanese nuclear power plant restarted. Please explain.
All right. And you teach them about what you did there in
Yes.
Fukushima, and not only in
About
Fukushima, in Japan.
About 600 people joining at Germany's huge hotels rooms, and I attend the meeting by online.
Wonderful. So
lot of people recognize the importance of the nuclear power plant and also importance of to increase the safety.
So
And
Germany is now thinking to return with the, shut down the power plants they made years ago after Fukushima. And right now they are thinking to return to nuclear, right?
Yes. The Green Party insists to stop down the nuclear power plant, but lot of people without ideology, they would like to start the nuclear power plant to recover the economy of the Germany.
I believe I've heard that BMW in Munich has said they have
Yes,
to have
also.
nuclear energy
Yes.
to keep being able to manufacture BMWs in Munich rather than in the US or Japan. Yeah. I would like to thank Isabela's questions are very important because we've learned that nuclear scientists need to have the public believe that they care about the public's interest before they care to listen to the scientists. And that's key to questions there. I would like to also mention that Professor Narabayashi has been instrumental in having the Japan Mechanical Engineering Society come to the U.S. and visit BWRs for almost 12 years. In fact, the January and December before the Fukushima accident, they asked ISOE to set up a meeting at Diablo Canyon to evaluate a new consideration for the Andreas fault. And 12 of them came. And then subsequent years, we've had representatives from each of the nuclear reactor, 6 nuclear utilities come and visit just for technical exchange to make sure they have the latest information on seismic qualification, on ASME standards, mechanical engineering, and that program. So that is quite remarkable, and to the credit that Japan ASME is very much involved in keeping the dialogue going with our operating engineers.
So the February, end of the January and February, Japan Society of Mechanical Engineers group visited Diablo Canyon. We watched the snorkel piping and that to protect the tsunami, and also the very tight, watertight hatches each rooms they had. We watched, but one month later, after, we had a very huge tsunami. So the Diablo Canyon nuclear power plant, by the earthquake occurred during the construction, and they posted the very tough building, and also a lot of safety measures such as snorkel piping, that cooling ponds. And so I think now it is very, very important to such a tsunami, natural disasters, and all the knowledge of the so I'm now 73 years old, and we should input the AI, our knowledge, and the watch the safety for each nuclear power plant. So I asked the Japanese old man, OB people, or the maker vendors, nuclear vendors, and also the utilities people, to please accumulate your knowledge and experiences. Also concerning ARARA, such as the maintenance during the maintenance outage.
Mm-hmm.
I think it is very, very important. Now we should do such a thing, knowledge gathering, to increase the nuclear safety increase and reduce the radiation dose, ARARA,
Mm-hmm.
and also the plant accident prevention. I think it's very, very important.
No, I think that's very good. I have a question for Isabella. I think that I am amazed how the nuclear experience with Fukushima and tsunamis has made the whole world much more concerned about the later tsunami after an earthquake anywhere in the world. It seems like I hear right away there's an earthquake somewhere in Malaysia or wherever, and then people immediately can be saved because they go to higher ground. So that's kind of a fringe, I would say, lessons learned globally of better awareness of tsunamis following earthquakes. Do you think that's kind of a public education success of the Fukushima severe accident experience?
I think so. I interned at Bloomberg in LA this summer, and we have a tsunami warning in LA. And one of the questions at the time was, should we call the nuclear power plants that we have here in California just to make sure that everything is set up? And I think this is something that Fukushima brought, the experience that you conducted in Fukushima brought to the whole world. Like, we started to think about the safety of nuclear power plants and how to navigate the situations of natural disasters. So I think that. But I want to also ask, because we have been talking about natural disasters, but when the situation, the risk is not a natural disaster, because we have seen like in the war, in the war with Ukraine and Russia, and we have nuclear facilities in a war zone. So how do you think this situation changed the way experts think about nuclear safety and radiological protection? I mean, Germany turning on the power plants again in Europe. So Europe is always in this situation of caution because of war. So how do you think about that?
In Japan, we started to making the nuclear shelter, even in the nuclear power plant. And also some obstacles such as the antenna and the transmission line tower. It's the hijacked terrorists couldn't attack the nuclear power plant. They died by antenna pole, the transmission lines. And also, I asked the Japanese government to make the self-defense force to make a missile to protect such a another country's missile, to attack, to protect such a missile attack. Because in Japan, each nuclear power plant has a self-defense force for such a basement. So the cabinet judged to prepare such a missile to protect the nuclear power plant.
Yeah, perhaps. Go ahead, David, please. Dr.
And I
Miller,
think,
please.
Isabel, the value of IEA International Atomic Energy Agency is the key international agreement organization to have a international law that gives a perimeter of 10 or 50 kilometers around each nuclear plant that may be in a war zone. The Ukraine plants are the largest ones, the largest consolidation of nuclear power in Europe. And of course, they're very valuable to those who control it. So it obviously is a target of a country who's trying to reclaim those nuclear power plants. But the IAEA General Secretary has been quite aggressive in being involved with making sure they were shut down, and they remain in cold shutdown, and that they agree not to have military action or bombing within that radius around any commercial plant. And that's what we need to make sure all countries agree and support.
Yeah, and I would like to contribute to this because it's quite, accepted that nuclear is a safe zone in case of war. So all the interested parts, which both parts of the war or more, so they know that the nuclear must be protected against hostile actions. So actually, even there in Zaporizhzhia, so that happened, but not in nuclear side. Some events, and actually the operation of the power plant, even for the shutdown situation, but the cooling system is continuing running well. IAEA experts are there, ensuring that the power plant is safe in a safe condition, so that the public never would be affected, because the war is a military situation. So civil nuclear power plant is not really the case, mostly because nuclear. So as David mentioned, naturally energy supply could be a target, but that we're talking not about nuclear generation, we're talking about energy transportation, things like that. But then is another thing. So, and there is a international law, there's international law establishing the behavior in which regards nuclear protection for the nuclearized countries. So, and yes, and we must to ensure, and all together we must to reinforce that nuclear is for the humankind, and that never must be touched by a situation of war. So this is just to contribute. But right now, we had some war over the world, even in some facilities that the public was protected. That happened some situation. The public in general was protected, was informed, and well advised. So that is not really the matter of this topic, but yes, thank you for your question. Yeah. So, okay. So let's go ahead. What more post Fukushima? So is Japan intending to build other nuclear power plants beyond the SMRs? I mean, I'm talking about big ones.
In Japan, we restarted the first priority, the current exist nuclear power plant restart. After that, we build some SMR or new nuclear power plant. Because in Japan also increasing the electricity demand. The Onagawa nuclear power station restarted. Kyokushia the memory semiconductor factory started. So and also the Hokkaido Electric Power Company's Tomari nuclear power plant. There's also the semiconductor company is under construction. 2 years after the factory restarted. So the economy of such a new industry helps the economic growth in Hokkaido area in Japan. And also, Kashiwa's career area, the Kashiwa's career 6 unit started. Some data center will be uh, built at the Niigata area.
Thank you. Yeah. So, and in the United States.
Marcus,
please.
I would like to also note that in light of AI interest, we need to realize the dialogue of technical exchange of information between our countries is so important. Brazil, the operating experience, Angola, and Japan. And I cite the late Walter Mitsumachi, went and got his master's at the University of Michigan Nuclear Engineering Department and won the Distinguished Alumni Award for he developed the advanced BWR. I was developed Fukushima is Mark 1 BWR, then there's Mark 2 BWRs, and Mark 3 was the Clinton. Only 6 were built, 4 in the US. But they were difficult. They were trying to make a BWR into a PWR. But Walter had the insight as chief engineer of Toshiba to develop the advanced BWR, which is much better, and it has been built in Japan because it has better controls with the severe accident scenarios. So I note that there's nothing that AI can do except the human element of exchanging these best practices worldwide, and hope that continues. And the key is that we have to have our own eyes as experienced scientists and engineers looking at every part of the plant every day to make sure that we're monitoring any type of leakage of coolant or steam leaks, etc. That's going to be the key to success. As you say, in the US, yes, we have a plan to build 200 nuclear 1,000-megawatt plants by year 2050 because there's concern that China will be up to 100 by then, as they are able to build within 7 years. And we take almost 15 years for Vogtle 3 and 4, which are our 2 newest units that just started in 2023 and 24. They're running well. They're the Westinghouse AB1000s, which 4 were built in China also. But we have new power plants such as Nuclear Power Corporation that's planning to build 1,000-megawatt plants throughout the U.S. And in addition to the small modular reactors.
Yeah, that's wonderful. I mean, and this is for you, Isabela, is very important to know because the huge amount of inversion that will happen, the budgets that will be provided to install those power plants over there, and more than that, the lack of human resources. So it's very important to think about the human resources, the preparation of new technicians, and in our side, necessarily radiation protection experts to support the safe operations in a power plant. So how are you doing that there? So I think that human resources for both Japan and the United States, I guess, is a key point. How are you dealing on that? You guys, I'm talking about the economics to Isabela, and for you, human resources training.
For our last symposiums, as we have every year in January, as you know, the Honorable David Wright, who is a commissioner and now is the chairman of the Nuclear Regulatory Commission, David Wright, has challenged us to go to the high schools near our power plants and encourage juniors and seniors to get involved in studying nuclear science and consider what we call the science STEM program, science, technology, and mathematics and engineering. And so we've started having our first high school NATC analysts work for us in the summer co-op program 2 years ago. And we've already had over 30 analysts who are undergraduates at University of Illinois, but now we're actually going into the high school level to get them interested in careers in nuclear power. And that's been very, very good for us to be challenged by the chairman of the commission to make sure we get the manpower we need. He looks at the columns of the small modular reactors and the expansion of nuclear power, and we only have about a third of the people we need in nuclear engineering and health physics to run those plants over the next 20 years. So there's a significant deficit of unless we beef up our programs. University of Illinois has the largest Fleischmann class in nuclear engineering ever coming in, so it's working.
And in Japan? Dr. Narabayashi, and in Japan, how are you dealing with the human resources? I mean, I guess you need more technicians, skilled technicians in nuclear, right?
Yes. But even soon after the March 11, yes. Even soon after the Fukushima Daiichi accident, a lot of students, excellent, very, very excellent students. I teach the student about 2,000 students. And excellent students, 5 students choose to take United States with ISOE meeting. And the students learn a lot of good practices in the United States. And such a student, excellent student, making the super engineer. At this September, I attend the ICAP 2025 in France, Antibes. 5 of my students have grown up the super engineer and making them the presentation. And also, our Tokyo Institute of Technology, also a lot of students are getting some exciting to make the new SMRs.
Thank you. Thank
Yeah,
you.
that's great. And from the
He's going to show something in his presentation.
Oh, this. Oh.
Yep.
Can you see this?
Yes, we can.
Oh. So this SMR,
Small modular reactor.
modular reactor, the design by the students. This 3D
It's a nice product.
design by student. Designed by the doctor course student. And he back to the Vietnam. Now he's a regulatory in the Vietnam engineer. So I think in near future, such a SMR will be built, export in Vietnam, I hope. A lot of students are very, very exciting to design such a new SMR.
Very nice.
Is this a startup? Is it
Yes.
a startup
Uh,
backed by venture
uh,
capital or something?
Yes, I make a company, venture company, GX Energy. I'm the founder of the GX Energy. Yes, it's a startup.
Interesting. Yes.
Mm,
So
yes,
a lot
and
of technology coming
and
from this.
some nuclear vendor join this project.
Very nice. Very
Mm.
nice.
You see,
So
one of the advantages of this is the cooperation. I know Ontario Power Generation and Tennessee Valley Authority have developed a program together along now. Poland has joined the partnership where they will put 20 to 30 out at the various sites they have in Canada and US. In the
This is
US example, they have a plant called Belafonte that
yes.
was 98% completed 30 years ago, but never started up. So it has the environmental permits to put a nuclear facility there immediately. So they're able to not have extended time to do the environmental assessment by regulators. They can simply now move the small modular reactors when they're ready in modular fashion to that site that's pre-approved.
G-Hitachi Belnova start construction of BWX 300.
Mm-hmm.
To tell the truth, I advise G-Hitachi for 2 years
Ah.
to increase the safety. I visited a lot of times with Minto.
So just reinforcing, when do you think that those SMRs will be available to start to operate? Since, I mean, after constructed and installed and start to operate. So
In Japan, there
yeah,
are
plus minus.
there are some site will be for the new construction will have some plans. I asked some nuclear utilities, electric power companies to build such a compact and load following nuclear power plant. There are some decommissioning plants, but the compact nuclear power plant will be built, can be built at the very near to the decommissioning plant.
All right.
So
Okay.
the site of the nuclear power plant in Japan is very limited. So the compact SMR, this SMR, not SMR, middle modular reactor, it's a 1 gigawatt electricity output and load following. So the high performance cost performance, also the weight and the volume almost half of the current BWRs. The students exciting to make 3D CAD and making compact.
Oh, I think so. So
Mm.
yes, this is very impressive. Well, and do we have an idea about the amount of money that could be spent to construct an SMR, at least for the beginning? Naturally, along the time, the costs will be reduced. But how much budget should be allocated or could be allocated or should be allocated to have this constructed SMR and operating? Do you have an idea because in the order of a giant power plant, 1.3 gigawatts, for example, installed power, so it's I don't remember well, but it's about 20 billion, right? And I don't know of dollars. I don't know exactly if this
I
amount of
that
money.
Japanese government to reduce the construction of the solar panels and also the wind turbine. The very, very huge money was needed. So the huge money to construct a nuclear power plant, much cost performance, much better, effective to increase the economy. This is the key point. Also, the President Trump to stop the wind turbine. Not necessary anymore. As I explained, solar panels and wind turbine is unstable. And also the capacity factor is very low. It is impossible to supply solar panels, wind, such a such a electricity, not sustainable. It needs huge money, but impossible. It's total 100% solar panels and wind. Battery or another fossil plant is needed because to compensate the shortage of electricity. So solar panels, wind never attain the 100% sustainable energy. Hydro and nuclear is the best solution. So to stop the budget to the such a sustainable solar panels and wind, change the such a budget to build a nuclear power plant.
Yes,
Right.
I can see that the Darlington site in Canada has indicated that the costs for a 300 megawatt Tadashi GE plant is 60% per megawatt compared to the traditional 1,000 megawatt plant. So it's 60%. And it takes 2 to 3 years for them to build the 4 Hitachi GE BWR X300s that are being ordered. Does that help you, Marcus?
Yeah, for sure.
Yeah. And I just want to add that the US also had a deal in October with Westinghouse, $80 billion partnership in order to build this power plants. And Japan has pledged $550 billion for US projects to support the US nuclear build out, potentially covering costs for the new reactors. So
yes, and I think the key here, Isabela, is that they're modular. So they can be built quicker and then moved to a site either by ship or by rail. And I'd like to note that one of the marvels of how GE and Hitachi had built the BWRs, I appreciate, is that every component in the existing 93 plants that we have one of the 6 planes, a ceiling, floor, or 4 walls. One of the 4 walls is always a block removable wall. So you can replace the tank, you can replace the pump. And that's the beauty of these plants that we plan to run for maybe 100 years. Most of the cost was rebar and concrete. You can replace all the piping, you can replace all the pumps and tanks on a cycle of what we call modernization every 20 or 40 years. And so that's going to be the value of our existing fleet, To add on the icing on the cake is the new small modular reactors, which are even more modular, which you can pop out, and they're passive. They are not susceptible to severe accident, and they're 60% cheaper per megawatt than the BWR or advanced PWR.
That's great.
Right. And that is also some projects in process that are touching on the micro reactors. So much lesser power output, but which could be transported in a truck or smaller yet, producing from 1 megawatt to 15 megawatts, something like this, to also to feed the energy, the needed energy for a small community, for example, far like in Amazon or close to. So because there is very difficult to achieve. So, but once very, very safe, a small modular reactor could be transported by river and give electricity to the communities living on the borders of the rivers, which are the majority of people, because in the jungle inside is, unreachable. You can't go. But the majority of the population, they lives on the borders, on the margins of the rivers that are planting their Amazon, but without good quality of life. So, and I'm not talking only about Brazilians. I'm talking about all the Amazon countries that are living there. So people living there, so like Colombia, Venezuela, like Guinea, say again, the Guyana, yeah. So we have lots of countries that people are living in very poor situation without electricity. We need to think to on those people. So they are very important. SMR and micro reactors as well, they are very usable for such kind of thing. Yep.
Yes, and those off the grid or small reactors are very unique and have a lot of promise. But I would think we should also talk about the engineering challenges. And that is that we are going to have all these different designs. And the key is to have standardized designs, if you can, so that we can basically quickly remove and have parts that are able to be changed out. And not, if you have so many different designs, the training costs to have the manpower trained to run all of them is very difficult. And the other part is to make sure that we have the ability to handle the additional generation by the grid. The Susquehanna plant that I started in 1982 and 83, 2 units, was the first to have a data center 4 years ago at their site boundary. It's been built. It's being used by Amazon, but there's a question on they still have to pay for the grid charge because even though it goes directly from the plant to the site fence that has the data center, there needs to be, the grid still needs to have some issues resolved from the regulatory basis of, is that allowed?
Right.
This
Okay.
SMR, it's a MMR, middle modular reactor. It's if the natural circulation, the electricity is 300 megawatts. But by using the interpumps, reactor interpump, the electricity power output 800 megawatts. And the G10 newest fuels installed at the core, 30% in power plate can possible. So 1 gigawatt, 1,000 megawatts is possible. This is a cost very, very effective. And also, the reactor building is a steel building. It's utilize a ship hull structure, making the technology of the ship. So this building is made of steel. So 100% construction at the factory and export by ship like this.
Right.
So
Yeah.
high quality construction is possible by the factory. After that, export it and connect the cable to the grid, to the country.
Yes, I think that's a very important point, Professor Narabayashi, because
Mm.
all these sites that have been abandoned, like in Germany, or in our case, Pilgrim and Millstone One, those have the incredible costly grid already connected to that site and environmentally approved for a modular reactor. And so we'll see that both in Japan and perhaps Germany, certainly in US and Canada, those sites that have decommissioned their units, Kawani, Zion, are perfect examples of places to put these modular reactors. You could bring one right through the St. Lawrence Seaway, right to Zion, where you already have a grid system set up.
Yeah, it will reduce a lot the costs for those new power plants, SMRs. So, yeah, you're right. I completely agree to you. So the existing grid, electrical grid, and also the site already approved, environmentally approved, actually it plays a very important role in this type of project. So yes, I agree. So it's a very nice opportunity, and it must be taken for the nuclear world. Yeah, nuclear utilities. So
No, moving to closing remarks.
yes, we will. Yeah, the time is going on. The topic is very, very exciting as well. We could have room to talk much more, but the time is going out. So I would like to give the words for you, the floor for you for the final remarks, and then I will at the end we conclude this meeting. I want to say that this meeting this panel should be translated for at least for Portuguese, but naturally English as well will be subtitled, and then it will make easier for you. English is all over the world. We have a different English in South Africa, Australia, UK, Texas, and David, and Japan. And actually, we must do something for our colleagues over the world to be able to better understand us. We will try to subtitle and then give to you the complete presentation of this meeting. It will be saved in our podcast on YouTube and also Instagram, Facebook.
Yeah, I just want to ask if there's anything that we didn't ask and you feel like it's worth mentioning. Anything left out?
Yeah, something that we would like to point out. Yes. You, David, and Dr. Miller, Dr. Narabayashi, please.
Yes, I'll let Dr. Narabayashi close, since he has such excellent presentations with detailed information in his slides. And it's very rewarding and gratifying to see the work he's done between the government, the local mayors, and the utilities to restart these plants. So I congratulate you very much on that. But my closing comment is we have to understand the importance of the human talent and skill sets necessary to meet this challenge that the data centers are giving us, the challenge of the public now realizing that there's a nuclear renaissance needed because it's clean energy. All of our nuclear plants in Illinois are called the Braidwood Clean Energy Center. The Crane Clean Energy Center is now the name for 3 Mile Island. So they can be our answer to global warming. But the most important thing is our training of talent, internationally exchanging information and valuing the ability to maintain our current fleet, in our case, 93 reactors, at the same time of building the new 1,000 megawatt plants and the new modular reactors. I'm very excited that in the US and Canada, the GE, Toshiba, or Hitachi 300X is the lead design that will be very important to be able to standardize within the North American area. And that the US at the University of Illinois, we are building a demonstration small modular reactor that will be used to train and research the small modular reactors, which go into operation in the next 5 to 10 years. Thank you.
Thank you. Dr. Narabayashi.
So I thank to the ISOE support to the Japanese restart of nuclear power plant, and also the growth of the super engineer students.
Yes, I can see there this nice picture.
So,
Very nice.
and also,
So, Isabela, take your time,
Yeah,
please.
just want to thank
And also,
Professor Narabayashi. Oh, sorry.
NRC also people suggest the Japanese engineer. It's very, very helpful.
That's great. Well, thank you, Professor Narabayashi, Dr. Miller. It was great having you, and thank you for sharing your knowledge and your experience with us. And thank you, Dad, for inviting me over to this podcast.
Okay. Thank you. So, we achieved the end of this presentation. Let me try to, João, nós estamos finalizando. We have just moved to Portuguese just a bit. So, we will conclude now our presentation, our panel here, but for sure, questions may come later, and I will address to you, Dr. Narabayashi, Dr. Miller, and actually also to Isabela, because we are always learning in nuclear, and I guess in everything, but in nuclear, this is a real truth. So we are always learning. And SMRs, I see, is one of that was raised here, and actually, I agree, is one of the best features for the future that we will have in terms of nuclear. So then I'm pretty excited as well to see the renaissance of a nuclear, and I'm prone to be part of this world as well. I never completed my life in nuclear. I want to go a bit more, so I will. And actually, we'll be together in the near future working on that. It was a real pleasure to have you here. I really thank you so much. You did very good. I hope to see you there in Clearwater next January. And actually, I will appreciate to talk more and better with you. Thank you so much. Thank you, everybody.
And thank you,
Happy New
thank
Year.
you, Isabella, for your input, and Marcus for putting this together. We'll see you January 13th through 15th in Clearwater.
Thank you.
Thank
My
you.
pleasure.
Happy New Year.
See
Bye
you.
now.
Bye.
See you.
So-
See you.